The Ferrari SF-25 is here. We recently got to see the car on track in Maranello during a shakedown test. And I have to say, there are a lot of really interesting aerodynamic features to go through, and the car has gone through quite a bit of change. So this aerodynamic analysis will be heavily focused on some of those changes, as well as what maybe some of those changes might be doing. For those of you that don't know me, my name is Dr. Obbs. I have a PhD in fluid dynamics, which means that I have a good understanding of how fluid structures interact in an aerodynamic sense. And so, typical disclaimer for all of my videos, there is no way of knowing for sure what everything is doing. We can simply use our technical understanding and technical knowledge to be able to make at best an educated guess or an understanding of what's happening, but it's impossible to know for sure what's happening without the computational fluid dynamic analysis or being a designer of the car. Let's jump right into it. So jumping right into this, this is a really good side-by-side shot of the SF-25 against the SF-24. I think some of the things that first jump out that we can see is there's quite a bit of extensive change to the forward part of the side pod. Ferrari has now integrated this McLaren-style front wing, which a few teams on the grid are actually choosing rather than more of this sort of overbite type design they had on the car in 2024. But this area is obviously very important, so we'll get into that. You can also see that the shape of the side pod is different compared to the previous year. There's a bit more of a bluff face here. You can see how wide the side pod is in this direction compared to how wide it is now in this direction. Some changes as well to the rear wing that you can see here as well. Much more aggressive on the cutout in the rear wing this year. Now, granted, rear wings are going to change as the year goes on, but there's obviously also some suspension changes as well in this front section. So if we just jump right into it, one of the first things I wanted to really focus in on is this forward side pod. Um, this forward side pod is really important because one of the things that you're going to naturally generate is you're going to generate some static pressure in the front part of this intake. So irrespective of whether it's from 2024 or 2025, this forward pressurization is actually really going to help to pressurize the top deck of the floor right here. Um, so you're going to be imparting some top pressure here, and underneath the car in these outwashing tunnels underneath the floor, you're going to be generating very low pressure or suction pressure. So what you're effectively doing is you're creating a pressure differential across the front part of the floor, which is effectively going to help you with forward balance. Now, this forward pressurization, there's multiple ways that you can do this. So one way is you can create a very kind of bluff side pod shape, right? I think that was one of the things that we saw a lot of teams were doing at the start of this regulation set was they were creating a very bluff shape, and that bluff shape was creating a lot of top pressure here because it's a bluff shape. It's not very streamlined, which was helping them with the pressurization. Now, obviously, that is not a very good thing to do if you want to have a very aerodynamically efficient car. So what teams have chosen to do nowadays is they've chosen to create this sort of shark inlet or the forward wing. And what's happening is all of this air that's coming off of the forward wing that's interacting with the front suspension and ultimately coming to the forward wing is all upwashing. It's all upwashing into the intake like this. Now, if you create sort of a wing-like structure in this forward portion right here, then essentially what you're doing is you're downwashing all of this flow, right? So you're creating a little bit of local lift in this region, but you're also, like a wing, creating a bit higher static pressure on the underside here. So you're effectively getting the exact same pressurization or static pressurization that you would get with a bluff side pod shape, but you're now able to also have this much more streamlined side pod profile which allows you to be much more aerodynamically efficient. So I think that this forward shape that Ferrari has created here is really just their best attempt to create that top deck pressurization in this region, and also to generally create some forward flow structures as well that we'll talk about here in just a minute. Closer to what's going on in the forward part of the car. I think the first thing to notice, and lots of teams are doing it, is that you have this sort of cyst structure in this region right here, where the floor is essentially as low as it possibly can be, right? And you know that because you actually have the side impact structure, which is actually protruding into the top deck of the floor. And why would you want to do that? Well, all of these tunnels, which are underneath the front floor here, are actually its own sort of venturi. So it's taking the air that's coming into the outer tunnels, it's squeezing it down towards the ground, and it's ejecting out. So you're naturally creating some suction from that. So you really want to be able to push those tunnels as low as possible to get much more inlet to exit contraction delta in the area. So you generate a lot more of a sort of a venturi effect, right? The other reason is that you're, again, coming back to sort of this pressurization, top deck pressurization. You're able to create much more outwash as well, which is one of the things you certainly want to do. So this pressurization is also acting as sort of like a pressure barrier, which is taking this upwashing air, especially the air that's on the edge of the forward floor here, and it's just outwashing it. So you're getting a lot of outwash, which is going this direction, but you're also getting natural tendency of flow to go into this undercut as well. Now, the outwash is really important because, as many of you already know, we talk about this quite a bit. You have a lot of front tire wake. So you've got a top wake, you've got a lower tire squirt or squish, and you've also got like sort of a mid-wheel wake. So we refer to this as lower, mid, and upper wake. So how you choose to kind of deflect that wake and move that wake outboard and keep it away from the downforce generating elements in the car is going to be dependent on a few different things. So firstly, we've always had these outboard fences here, which are very important for creating some pressure as well, because they're sort of facing the flow, and they'll create some pressurization, and that pressurization will also help to outwash any air that's coming through here and keep this lower tire jet outboard. Now, whether or not this mid-wake is also being managed by that, hard to say, again, because don't have the CFD, but it's really this upper wake here, so this upper tire wake that you're really worried about. Because this upper tire wake is either going to attach itself to the body, and it's going to come down into your rear coke in this region over here, or maybe it might get ingested into your intake. Probably this upper tire wake is not going to make it into your floor, so you don't necessarily need to worry about that. It might get pulled down into your G line around here. So what you're doing in this region is very important. So I think one of the things that Ferrari is doing really well, actually here as well, is they've created a few really unique structures. So they've got this little kind of I want to call it a winglet, which is out here. You're also going to shed some vorticity off of this wing here because it's higher pressure on the bottom. So that's going to kind of be outwashing on the top. No, sorry, it's going to be outwashing on the bottom and washing on top. So maybe that's going to also help. But we've got a better shot in another angle here to be able to see. But really, this whole shape of the top of the side pod is primarily there. The bluff nature of it is there to manage this upper wake, upper tire wake. But I didn't want to obviously miss the opportunity to talk about the importance of the changes of this top deck. So you've also got this little stepped feature here. Kyle Engineers did a good job of talking about this. I've talked about it in the past, vortex discretization. Sometimes it's easier for these vortices to stay alive when they're discretized or smaller, rather than having larger vortices that ultimately uh, interfere with adverse pressure gradients and get lossy and blow up. So maybe this is just an attempt to do that. But this top deck area here and the pressurization of this top deck region and the amount of outwash that you want to drive in this direction, working in tandem with the outwash that you're getting from this outer fence, the outwash that you're getting from the outer tunnels, as well as the air is coming out, all in an attempt to really manage the front tire wake. A bit deeper into what's going on with SF-25 from the front to back. Here, if we just revisualize the tire wake structures, you can really see how the side pod shape itself is, they've maintained some of this bluff side. They've now got a bit of a deeper V in here along the G line, it appears like, because the natural bottom of this side pod is higher than it was last year. You're going to naturally have more volume down here in the bottom to be able to pull some of that G line undercut flow to the back, where you can really energize. You can energize the rear quarter, for instance, here, because you're getting some fresh air that's coming down into the floor and being ingested into the back. You also can send some of this G-line air down back to the top of the diffuser, which is going to help with diffuser extraction. So there's a lot of reasons why you would go that direction. But I didn't want to spend the whole time really talking about that. I wanted to really focus on the front part here. So the choice for the more loaded inboard wing, which last year, Ferrari was sort of, they were inboard loaded. They were sometimes mid-loaded as well. But certainly, if this is an indication of the direction they're going to be going this year, then it's important to notice that they have decided to have more inboard loading. But we can also see the change to the pull rod style front suspension as well, which is a big change from them where they were previously push rods. So this is aligning more with what Red Bull and McLaren have done as well. So now focusing in on that, that's really what I wanted to talk about. So one of the things that is probably not talked about enough is that anytime that you have a solid wall, and then you have a structure that ties into that wall, like a suspension arm, you're going to get what's called aerodynamic junction losses, because anytime that you have like this region where you have 90-degree angles, or you have abrupt geometrical change, you're going to generate a lot of loss structures. And these loss structures are obviously not good, especially in the suspension area, where you want to have as clean a flow as possible, because all of this flow is ultimately going back to your side pod. It's going, again, like I mentioned before, it's going to your top deck, where you're going to generate some outwash, and some of the lower flow structures are going into your floor. So you really want this flow to be as clean as possible. And what aerodynamicists and engineers do is that they create these little, if we redraw this junction, they create these fairings, right? So they try and make that junction as smooth as possible, and this goes all the way around that fairing. So you give yourself a nice, smoother flow transition to be able to pass the air over. But the issue is that it's never perfect, right? You're still going to generate some losses in this junction area. We call these junction losses. Now, if we think about this in context with the change to the pull rod suspension, what you will see is that that junction is much lower. So that junction is here. You can't do a lot with the junction losses that you're going to get from the upper and the lower A-arms, etc. I mean, you can do something obviously with the junction that you have here. And in this region, if you're going more anti-dive or whatever, then you're going to put those junctions a little bit lower in a sense. But if we just kind of focus in on that point there, because with the pull rod suspension, this junction is lower, what you're going to want to do now, and the aerodynamic gain is that you've opened up effectively this whole region where you can upwash this flow from the front wing. You can drive the front wing a bit harder inboard. You can upwash it through this slot right here. And on top of that, you're going to hopefully avoid some of the junction losses that you might get from this lower junction. Now, alternatively speaking, if you're in the push rod configuration, then what you're going to do is as you're upwashing that air, you're going to get more junction losses higher, and those junction losses are probably going to be ingested downstream. But strictly speaking, in this sense, the important thing to notice is that it's one of the reasons I believe that you would sort of be restricted to have to run more inboard front wing loading because you want to effectively pull this air up higher than this junction and try and kind of thread the needle in essence to get it between the upper and the lower control arm so you have as clean a flow as possible. A better view just to be able to see how much of a space you have here to be able to upwash that air and pull it through sort of that gap between the top control arm and the lower control arm. And now you've got the point for the pull rod suspension, which runs like this. And you're hopefully going to be able to sort of minimize some of those junction losses that you would get here. You can see really well, actually, these fairings that I was talking about here in this region, just to helping to reduce the junction losses that you're going to get here that are going to be ingested downstream as well. But, I think we can very clearly see. Now, I have noticed people talking about anti-dive suspension choices. You can see, the anti-dive geometry here for the Ferrari. It's not as aggressive as a McLaren, and I would hazard a guess to say it's maybe not as aggressive as the Red Bull was in the RB20 last year, but I think it's being a bit overstated on how much this can help you to turn the flow. The angle of and the position of the leading edge of these control arms is highly regulated by the regulations. You can't have an incredibly negative angle of attack, for instance, to the incident flow, nor would you really want that because you then really, lead yourself to a point of potentially for flow separation across the controlling arms themselves, which is obviously not good. But they are using this to help sort of progressively in sort of a stacked sense help to gently navigate this region to push the air down so it gets into the top deck and obviously into the floor itself. I think the other thing to notice is that you've got, I was talking about the inboard loading as it relates to the outwash, but then as you pull down the outboard portion of this front wing, what you're also doing is you're reducing the pressure differential between the top and the bottom, which means that you've got a much higher differential inboard. And the positive reason for that would be that is going to help naturally this air to want to gravitate towards the region of suction inboard of the tire, which is potentially also going to help you a little bit with tire squirt, controlling the inboard tire squirt. So down here, we've got this, tire jet that we talked about, same tire jet on the outboard side. And it's really this inboard tire jet, which is a big problem because the inboard tire jet is, you don't want that to get ingested into your floor. And so for that reason, anything that you can do to sort of preferentially push the air inboard and drive as much energy into a low energy structure like a tire jet is just going to help to dissipate it faster. So that would be one of the added benefits of being able to go to a more of a pull rod configuration, having to now load the front wing more inboard and offload it outboard, which also kind of gives you that preferential flow from outboard to inboard. So the other thing I did want to talk about, we kind of cast our eyes to the rear of the rear wing, is that it's got an incredibly aggressive cut in the rear wing. So Nowadays the rear wing cuts sort of look like this, and you've got, the side of the wing, you've got uh, the primary and secondary elements like this. But this actual cut of the rear wing is getting incredibly aggressive nowadays. So I've talked about this before in another post. So I think that what this does is it helps you to kind of share the vorticity across two shedding edges like this. So you're going to generate some vorticity around this edge and this cutout edge as well, which I think my perspective on this is that it's just helping to reduce the overall vorticity across both edges there. Whereas, if you had the alternative that teams were running last year was that if you look from the top down, you kind of had more of a shape like this from side to the rear wing. So this is the rear wing, and this is the end plate here. And you always got this sort of a weird dead zone in this region here where there was not a whole lot going on. And I think what this was doing was negatively impacting the load across your rear wing. So if you looked at the amount of downforce that you could generate across that rear wing, you would have very high load across the central section, and you would have basically very low load. And it would get lower and lower as you got more outboard because of this recirculation region. But as you cut out the rear wing now, it allows you to effectively load the span more uh, from middle to out. Image is certainly by no means a perfect one. It's really difficult to find pictures where you've got the right angle and the right scale to be able to do a side by side. So if we just take this for what it's worth as a way to be able to see how the car is different from front to back, I think it tells the story that we've been talking about. You can see in this front wing, like I was mentioning before, you have more of a kind of an even loading across. You can also see the push rod compared to the pull rod. You can see the junction up higher here, which might have been one of the reasons why you might have needed a bit more um, kind of management of the boundary layer, management of some of these junction losses, and kind of bleeding that off in this sort of upper intake. This upper intake to me looks to be a bit smaller than maybe it was last year. I could be totally wrong, but you can really see the difference in the intake shape here. This now shape is actually going opposite to the direction that a lot of teams are going. A lot of teams have gone the direction of having this almost be a letterbox style, as small as possible. That's really what Ferrari was using. And that's just because, again, you're using as much shape and structure here to create that top deck pressurization. But we should acknowledge also that even though you have an inlet here, there is a restriction through this entire cooling system because this is an inlet. The outlet is somewhere back here, right? They've got spine outlets. They've got an outlet on the engine cover in the back here. So the intake pressure compared to the outlet pressure is ultimately going to dictate or tell you what the flow resistance is through this circuit. And that flow resistance is ultimately going to determine what the intake static pressure is, along with a lot of the surrounding structures as well. So even though you have an intake here, it's not like you're losing all of this static pressurization that you would want. You're still getting this static pressurization. It's just maybe not at the same level that you would get if you had a solid structure, but you are still getting some of that static pressurization. But I think the other thing that this shows is how you have this top wing here. You can really see it looks like a top wing. It's very downwashing. Last year, you didn't necessarily have that sort of downwashing top wing. That's going to help you to downwash or pull more flow down into this gully that they have on the side pod. So that's one thing. The other thing is you've got, again, you can see really well now this, you know, I don't even know what to call it, but it's like front edge winglet. Um, and you should again have higher pressure in the bottom here, and you should have, sorry, you should have higher pressure on the bottom. You should have lower pressure up here, especially because you got the downwashing. which means that you would naturally kind of spool up some vorticity that would be flowing in that direction. So I think that it's possibly for the same reason that you would put one of these winglets on a wing to help with aero efficiency. Maybe they're doing that. They're just trying to, as much as possible, prevent that spool up of that vorticity along the winglet. Even though it's there, you're still going to generate kind of a sheet vortex around this leading edge. But maybe they're just helping to sort of, I don't know, control where that vortex is detaching or potentially reduce the strength of that vorticity as well. But yeah, I think this again shows really well the upwashing that you're getting here. It also shows, front wings. All the front wings nowadays are all outwashing. So I think that is important from an inboard to an outboard standpoint as well, because that's going to help you manage some of this, again, mid wake, top wake, probably not as much the upper wake or the lower wake from the front tire, but that's also going to help you pull out some of this as well. Doesn't seem to be a whole lot of difference in the nose structure itself, so you still got a detached front element here. But one of the things that is doing is it's also helping to sort of, the nose cone right here again is also helping to create some stagnation or some static pressure here, which again is going to act a bit like a pressure barrier, and it's naturally going to push air down under the wing here, which is again what you need to be able to then upwash this air to feed into all your downstream structures as well. So really cool design. I say, I'm really excited to see what Ferrari's doing with the SF-25. It's a lot of changes, but I think ultimately what they're trying to do here is, when they made the decision that they wanted to go to a pull rod front suspension, it just necessitated a lot of other changes, because of the fact that now you can drive the front wing inboard a lot more, because you've got that junction lower, you've got a lot more of this region that you can pass nice clean air through. It just necessitated some side pod changes to really optimize how that upwash interacts with the side pod, and ultimately the efficiency of the car itself. So I think all these things are related to one another, and I think just that singular decision is really going to allow Ferrari to ultimately optimize the whole car. So I hope you enjoyed this analysis. Be sure to follow my YouTube page for more on other cars.